Hello, in this video we'll talk about how the electron configurations lead to the periodicity of the periodic table, and then a couple irregularities you need to know, and then also we'll talk about some periodic trends you need to know. Okay, so the main idea here is that elements in the same column of the periodic table have the same valence electron configuration. So if you look at fluorine and chlorine, well, they have the same outside electrons, the valence electrons, and then just different amounts of electrons on the inside in the core. But the electrons on the outside, the valence electrons, they determine the reactivity. And so if the electrons are the same for fluorine and chlorine, well, then they're going to have fairly similar reactivities and properties. And so the periodic table was originally put together experimentally, just by looking at properties and reactivities of elements. And then once we learned electron configurations, then it started to make a whole lot of sense why the periodic table was put together that way. So here's one resource, a picture from one book of a bunch of electron configurations of elements. And then here's the one from your book, which I think serves better to illustrate our point. So if you look over here, here's fluorine and chlorine that we talked about with the same valence electron configuration. Just different energy levels, but overall 2 in the s and 5 into the p orbital. And generally, if you go left to right along one of the periods, one of the rows, you'll see that there's a pretty straightforward change in electron configuration. All of these fill the 2s with 2 electrons, and then it's 1, 2, 3, 4, 5, 6 into the p orbitals, depending on which element you're in. So that makes perfect sense. However, there are some irregularities in how electrons fill in the periodic table, and there's one set I want you to know. So here's the picture that describes that. So the 2 with the arrows pointing at them are irregular, the other ones are regular. So I'll talk about the regular ones first to kind of set the stage here. So when you're looking at scandium and yttrium over here, you would expect that they'd fill 2 electrons into the s and then 1 into the d, as they do, right? And then if you go to titanium, it's 2 into the d, vanadium 3, manganese over here is 5. Okay, that makes sense. As you keep going, 6, 7, 8, 9, 10. Perfect, that all makes sense. So those are the ones that are regular. Now, the ones that I kind of skipped over in that last counting are irregular. So if you look at chromium and molybdenum, they each have 1 electron in the s and 5 in the d, which is not what you would expect. You'd expect it to be 2 electrons in the s and 4 in the d. So it would, should look something like s2d4, like that. And it doesn't. So that's an irregularity. And then the same is true over here. You have s1d10 for copper and silver. Why is that? Well, there's a special stability from either a completely filled or a half-filled subshell. So here's another way to look at it, that the chromium valence electrons, there's only 1 in the 4s, but in doing so it can put 5 electrons into the 3d and completely half-fill that subshell. And for copper, if it leaves an electron out of the 4s, well then it can completely fill the subshell, and that's preferred. Even though it costs a little more energy to promote the electron from the 4s up into the d, it gains that energy back and a little more by having this half-filled or filled subshell. Okay, so that's the irregularity I want you to know. There are plenty of other irregularities in the periodic table that you don't need to know, but I highlighted them here in case you find that interesting. And there we go. So the next thing we need to talk about in this video is some periodic trends. Now, previously we talked about ionization energy, where the first ionization energy increases as you go up and right in the periodic table. And, okay, we need to talk about some other trends while we have some insight into the periodic table and atomic structure and electronic structure especially. So first up is radius. So it's kind of hard to measure the diameter or radius of an atom by itself because the electrons aren't a solid sphere. They have some probability of existing in some place, but it's not like you have a ball, for instance, or something like that. However, in a solid, when all your atoms are packed together, you can measure the locations of the nuclei very well. So we define radius to just be half the distances between the nuclei in a solid. And that's something that we can experimentally figure out. Okay, so if you look at the trend of atomic radii, it's generally highest for the alkali metals, lithium, sodium, potassium, and lowest for the halogens. And then as you go from lithium to sodium, potassium, it also gets bigger. All right, and then here's the reason why. So as you go, and there's also a summary of the trends too. So as you go down a column, your radius gets bigger. And this one makes sense because, well, you're putting electrons into bigger and bigger shells. N equals 2 is bigger than N equals 1. Now you're filling it with electrons. That's going to take up space. So as you go down the column, the radius increases. All right, that one makes sense. Now, as you go from right to left, the radius also increases. And here's the reasons here. Okay, so electrons are in the same shell, but in the same shell, okay, so say, electrons are all in the N equals 3 shell. That's the same size regardless of how many electrons are in it, more or less. But when you're over here on the right side, you have a much higher nuclear charge to hold that in, right? 'Cause positive and negative attract each other. So they'll hold tighter when you have a higher positive charge, but then they hold more loosely on the left side where you have a lower positive charge in the nucleus. So radius increases as you go left and increases as you go down. And in your head, you can think that this is just the opposite of ionization energy and that this increases when you go to the bottom left as opposed to ionization energy, which went towards the top right. Okay, so that's one trend you need to know. And here's an example problem, and I'll let you do this for the pop-up question. Now we're back to ionization energies. So we talked about this before in the previous video. Feel free to look that up if you have any questions about ionization energies. And so here's the trend again, right? Your ionization energy as you go up the column, and it increases as you go to the right. But when we first talked about ionization energies, we were using them to motivate our discussion of electronic structure and the atomic structure. Now we know that, let's revisit it and see why it makes sense. So as you go up a column, your electrons are in smaller and smaller shells. Well, I was trying to draw a box. Let's just do that. There we go, there's a box. Electrons are in smaller and smaller shells, and so then they're more attracted to the nucleus and just they're harder to remove, right? Your outermost electron is a lot closer to the positive charge when you're up here than it is when you're down here. Just physically closer, and therefore it's harder to remove. Then when you go from left to right, your ionization energy increases because kind of the opposite logic of the radius. Well, your electrons are the same distance from the nucleus, roughly, but now there's a greater positive charge, and so the greater positive charge holds the electrons to the nucleus more strongly and makes them harder to remove. And then it makes sense why this all works with the periodic table. Okay, and that's what I have for now. Thanks for your attention, and keep studying.